Last time, we introduced eigenvectors and eigenvalues. Today, we'll see how these can be used to understand matrices in a simple and intuitive way, and how this leads to principal component analysis. So our main result today will be the spectral decomposition theorem, which tells you how a matrix can be rewritten in a different way, solely in terms of its eigenvectors and eigenvalues. This is a very powerful tool of data analysis. So let's start by quickly reviewing our motivation. Here's a simple 2D data set, and the two features are correlated, which is a little bit of a complication. But what if we switch to a different coordinate system? Something like this one. What if we switch to these axes? So first of all, what would this entail? Well, let's take a point, say this one. In the original coordinate system, this might be something like 1, 1. In the new coordinate system, what would this be? Well, it would be this length over here, which maybe is something like 1.4, and this height over here, which is approximately 0. Two different representations for the same point. Now, the way we move back and forth between these representations is in this case just a simple rotation. It's a simple linear transformation. What is the advantage of this alternative coordinate system? Why might we want to work in that basis? Well, if you tilt your head a little bit, you'll see that in this alternative representation, the two coordinates are actually uncorrelated. That correlation goes away. In some sense, the data becomes a little bit simpler in this alternative coordinate system. And therefore, this alternative basis might be a natural place in which to do data analysis. So what are these natural coordinates? So this led us last time to the notion of an eigenvector. For any d by d matrix M, an eigenvector is a vector u that is sent by n to another vector in exactly the same direction. And the scaling factor, lambda, is called the eigenvalue associated with u. Now, what we saw is that the eigenvectors constitute a basis. Okay, so specifically, if we take any symmetric matrix M of size d, a d by d matrix, then it has d eigenvectors that are orthonormal. So each of them is of unit length, and they're at right angles to each other. Their dot products are 0. And we can therefore think of u1 through ud as the axes of an alternative coordinate system. It turns out that a matrix becomes quite simple if rewritten using this coordinate system. And let me explain what this means. Okay, so we take any symmetric matrix M. As we've seen, it has these orthonormal eigenvectors, u1 through ud. What we can do is to create a d by d matrix, U, whose columns are the eigenvectors. So the first column is u sub 1, the second column is u sub 2, all the way to u sub d. And in that case, U transpose looks like this. Its rows are the eigenvectors. Okay, so U and U transpose. We can also write down a diagonal matrix, lambda, of all the eigenvalues. If we do that, then it turns out that M is exactly U times lambda times U transpose. So first off, this means that M can be recovered exactly from its eigenvectors and eigenvalues. The eigenvectors and eigenvalues contain all the information in M. But the second thing, and the more remarkable thing, is that M is much simpler when expressed in this form. Okay, so in what sense is it simpler? I mean, we started with a d by d matrix, and now we have 3 D by D matrices. How is that simpler? Well, just look at these matrices. Each of them is very understandable. It's very clear what each of them is doing. U transpose is simply a basis change matrix. It's converting from the regular coordinate basis to the basis of the eigenvectors u1 through ud. U is the basis change in the opposite direction, from the eigenvector basis to the regular coordinate basis. And lambda, well, that's just a diagonal matrix, so it's just scaling each coordinate separately. M is simply the composition of these 3 elementary operations. So here is exactly what M is doing to any vector x. It starts by applying U transpose to it. So it takes x, which is a vector in our regular coordinate system, and then it applies U transpose to it, which basically converts it into its own basis, the basis of the eigenvectors. So that's step 1, U transpose x. Then it applies this simple scaling. Now that the point is in its own coordinate system, it simply scales each of the coordinates separately, lambda 1 through lambda d. And then finally it takes that answer and converts it back into the basis we understand, the regular coordinate basis. So any matrix can be expressed simply in this way. Okay, so let's see how the spectral decomposition theorem applies to this matrix M that we saw last time, this 2 by 2 matrix. So what we did last time is to figure out its eigenvectors and eigenvalues, and this is what they turned out to be. So now let's go ahead and apply this theorem. So we construct the matrix U, whose columns are the eigenvectors. So let's pull that that 1 over square root 2 out. Okay, the first column is the first eigenvector. The second column is the second eigenvector. Now U transpose, just the transpose of this, so its rows are the eigenvectors. And lambda is just the matrix, the diagonal matrix of eigenvalues. So it is -1, 3, 0, 0. Now let's go ahead and compute the spectral decomposition, U lambda U transpose. So as usual, we can bring the constants in front. So we have 2 square root 2's, that just becomes a half. And our matrices are 1, -1, 1, 1, -1, 0, 0, 3, and 1, -1, 1, 1. Let's start by doing these two. What do we get? We have -1, -1, -3, and 3. And now let's multiply those two matrices. So we get -1 plus 3, 2. We get -1 minus 3, so -4. -1 minus 3, -4. And -1 plus 3, 2. And so we indeed get back M. Okay, so we had this matrix here, we had this matrix M, and we were able to rewrite it in this intuitive way in terms of these 3 elementary operations: a basis change, a scaling, and moving back to the original basis. Okay. So now let's break the operation of the matrix as a linear function down into these 3 components: the basis change, the scaling, and then the basis change back. Okay, so suppose we are applying the matrix M to a vector 1, 2. What exactly is going on? Okay, so we can also write N as U lambda U transpose. And the first step is to apply U transpose to this vector 1, 2. What that does is to take the vector 1, 2 and rewrite it in this alternative eigenvector basis. Okay, so the eigenvector basis in this case has vector u1, which is 1, 1, and the vector u2, which is negative 1, 1, all divided by square root 2 to normalize them to unit length. And what we're going to do is to take this point 1, 2 and rewrite it in this basis. Okay, and so these will be the values we get. The first coordinate will be that length, and the second coordinate will be that length. So what are these values? Well, we just need to compute U transpose times 1, 2. Okay, so let's figure that out. U transpose times 1, 2 is 3 over square root 2 and negative 1 over square root 2. Okay, so this distance here is 3 over square root 2, and this distance here is 1 over square root 2. And that is the representation of this point in the new basis. Okay, so we've done this part so far. Now we're in the natural basis for the matrix. And in this natural basis, all we need to do is to scale the coordinates separately. Okay, and that's what the matrix lambda is doing. So what it's saying is take the first coordinate and multiply it by negative 1. So we get negative 3 over square root 2. And take the second coordinate and multiply it by 3. So we get 3 over square root 2. So in this direction we go negative 3 over square root 2. And in this direction we go 3 over square root 2. So we're going to end up somewhere over there. Okay. And finally, we return to the original basis by multiplying by u. And let's see what that gives us. Okay, so here's u over here. 1 over square root 2 times 1, negative 1, 1, 1. And then we multiply the vector we have over there, negative 3 over square root 2, 3 over square root 2. And what do we get? Let's see. We get negative 3 over square root 2, negative 3 over square root 2. So that's negative 6 over square root 2. Okay, so we get negative 3 and negative 3 over, so negative 3, 0. And that's the answer in our original coordinate axes. Okay, so now let's see exactly what principal component analysis is doing. So we begin with a bunch of data vectors x, and our first step is to compute their covariance matrix. If the vectors are in d dimensions, then this covariance matrix is a d by d symmetric matrix. And this matrix captures all the correlations between the features. Then we go ahead and find the eigenvectors and eigenvalues. How do we do that? Well, we basically ask the computer to do it for us. There are standard packages that just take the matrix and give us back the eigenvectors and eigenvalues. Okay. And since it's a d by d matrix, we get back d eigenvectors, u1 through ud, and the corresponding eigenvalues. Now these eigenvectors are the axes of the natural coordinate system for this data. They're an alternative basis in which we can represent this data. Okay. And in this alternative basis, the coordinates are uncorrelated. Okay. Moreover, in terms of what these eigenvalues mean, the variance in the direction u sub I is exactly the eigenvalue lambda sub I. Now, what we want to do in principal component analysis is to project down to a certain number of directions, say k directions, while keeping as much of the variance as possible. So what we do is to sort the eigenvalues into decreasing order, the largest eigenvalue, second largest eigenvalue, and we just keep the top k directions, u1 through uk, and that's our projection. We project a vector x in d-dimensional space to x dot u1 all the way to x dot uk. Onto the first k of these directions. Okay, so what is the covariance of the projected data? Let's see. So the first coordinate of the projection is the projection onto u1, and we've seen that the variance in that direction is lambda 1. The variance in direction u2 is lambda 2. The variance in direction uk is lambda k. And in these directions, U1, U2, and so on, in these directions, the data is uncorrelated. So the off-diagonal entries are 0. And so this is the projection. The projected data has this k by k covariance matrix. Okay, so that's it for today. We've finally seen the spectral decomposition theorem, which is a very powerful tool of data analysis. It gets used in many different ways, some of them very creative. And what we've tried to do today is to communicate a basic sense of what it's about. See you next time.